السلام عليكم ورحمة الله وبركاته. I will share my screen. All right. So we'll continue from where we stopped. Okay. Remember, today we have quiz during the last 10 minutes. We'll stop at 10:30 and then we'll take quiz for 10 minutes. Okay. We'll stop at.
How many questions for the quiz?
Not many, maybe just around 2. Yeah. And it is file in. Okay. The question is file in, which means you are going to solve the problem, then scan and upload on the blackboard. Okay.
Okay, then we want more minutes, not only 10 minutes.
Yeah, that's why it's 15 minutes. So 10 minutes for solving the problem and 5 minutes just to scan and upload back to blackboard. So altogether, it's timed at 15 minutes.
I wish you increase it because it's first quiz and this content, fluid mechanics. So we don't know how it will take. I wish you increase the time.
It is going to be simple. The time is enough. Just wait and see the question first.
Yes, but you know, it is the first quiz and this course and fluid mechanics. So we don't know how many it will take from us.
Yeah, I know the time that it will take. But I gave it 10 minutes. Don't worry. I know the time that it will take. It will not take more than 10 minutes. Okay?
Inshallah.
Yeah, it will not take more than 10 minutes. It's a very simple question. Okay? And all you need to do is to get your paper, write your ID, question number, solve, and then take a picture and come back and upload on the blackboard.
Okay.
Okay?
Okay. Thank you.
All right. So let's continue. If you remember in our previous class, we discussed about viscosity, okay, which is the ease with which liquid flows or the resistance of fluid to shear deformation. And this we said is synonymous, is synonymous with the friction in solid, okay? It's synonymous with the friction in solid friction. In liquid or fluid, we call it viscosity. Now we will look at another property, bulk modulus of elasticity. The symbol for it is E subscript V or kappa. Kappa. That is not K, but it's called kappa. Okay? Which is like a measure of the compressibility of a substance. Okay? How easily the substance is compressible. When we talk about liquid and gases, we have been talking about their compressibility, how the volume can change. Okay, the compressibility of any substance is a measure in terms. Is measured in terms of bulk modulus of elasticity, which describe the variation of volume with change of pressure. That is when you apply pressure, how does it change? Okay. Yeah, how does it change? And the bulk modulus, it is called, kappa is called coefficient of compressibility, or the bulk modulus of compressibility, or the bulk modulus of elasticity. Okay, we have Young's modulus in physics for solid. We have Young's modulus, whereby stress is proportional to strain. Yeah, stress versus strain. So the coefficient there, you have Young modulus. Okay, so here we call it bulk modulus of elasticity, because it is behaving as if the fluid is elastic, meaning you can pull it. Okay, so bulk modulus of elasticity of water is 2.2 giganewton. Giga is 10 to the power of 9, that is 1 billion. Okay, giganewton per meter square, very high, meaning water is almost incompressible. Okay, for gases, the value will be very small. Okay, because gases are all compressible. So if the volume of a given mass can be changed by applying force, then that material is said to be compressible. When you apply force, if the volume can be changed, okay, because when you apply force, you are essentially applying pressure, okay? Otherwise, it is incompressible. We mentioned that pressure has little influence on changing the volume of liquid. We took example of water whose volume changes by 1% when you apply a pressure of 210 atmosphere. 210 atmosphere, that's very huge pressure, okay? And the volume change is just 1%. You can compare that to air, okay? When you apply a pressure of just 0.5 atmosphere, the 0.01 atmosphere, the volume changes by 1%. Okay, so gases are highly compressible while liquids are almost incompressible. Okay, now this compressibility is considered at constant temperature because you have two types. You have the compressibility at constant temperature and the coefficient of volume expansion, which is the compressibility now at constant pressure but variable temperature. Okay, so in this case we are assuming that the temperature is the same. Okay, so the compressibility is given as, you know, it, you want to say something? You want to say something?
No, by mistake, sorry.
Okay, so it has been found that the fractional change in volume is proportional to the change in pressure. Okay, is inversely proportional to the change in pressure. Okay, it's inversely proportional to the change in pressure, meaning like if you apply pressure, the volume, the fractional change in volume will increase. So not inversely, but directly proportional to the fractional change in volume. Change. The fractional change in volume is dV over V. V is the original volume, while dV is the change in volume. So the change in volume over the original volume is called the fractional change in volume. Okay, and it is defined as minus dP over dV divided by V. Sometimes it is written simply as kappa equal minus V dP over dV. Okay, because this V will go up. Okay, so now what does this mean? You know, and like I mentioned, this is at constant temperature, so that's why we put T here, meaning the temperature is constant. And if you look at it, volume, the unit of volume will cancel volume, then we have pressure. So the unit of the bulk modulus of elasticity is Pascal or Newton per meter square, or you know, the unit of pressure, it has the same unit as pressure. Okay, and because volume is related with pressure, or sometimes we call it specific volume. Okay, specific volume is just simply the volume, or the specific volume is volume per unit okay, is the volume per unit mass. Okay, okay, it is the volume per unit mass, and volume per unit mass is what? Is 1 over density, because density is mass per unit volume. Okay, density is mass per unit volume. Okay, so with this relationship, that is the specific volume is 1 over density. Okay, when you substitute V here as 1 over density, you will arrive at this one, okay? Because you will realize that dV over V minus dV over V is equal to d rho over rho, okay? So when you substitute this here, you will arrive at this one, okay? Which is showing the change in pressure, okay? The change in density when pressure is applied, okay? And like I said, for liquids, it is incompressible, so the value of K is very high because dV is very small, no matter the amount of pressure added. So K is very high, okay? And then we have the inverse of the coefficient of compressibility, which is called the compressibility, okay, or isothermal compressibility alpha. It is designated with alpha, which is the inverse of the coefficient of compressibility. So alpha is just equal to 1 over K, okay? And then we have, like I said, the other part. This is at constant temperature, okay? Then what about at constant pressure? When the pressure is the same, but the temperature changes. Okay, temperature has even, if you remember, I mentioned when discussing about density. When talking about density, I mentioned that the density of a fluid in general depends more strongly on temperature than it does on pressure. Pressure affects the density of fluid more than temperature. Temperature affects the density of fluid more than pressure. So that's why it's also good to understand the coefficient of volume expansion, which is now, giving us the expansion of the fluid when the temperature changes at constant pressure. Okay, so this is very, very important because this particular issue that is changing the change in volume when the temperature changes, it has significant influence on a lot of processes that takes place. Okay, the variation of density with temperature is responsible for numerous natural phenomena such as winds, currents in oceans, rise of plumes in chimneys. Okay, chimneys, the exhaust in your houses, sometimes long exhaust like a tower where the gases escape, okay, from the kitchen. Okay, and that is as a result of the change in temperature, because when gases are heated, they become lighter, and when they become lighter, they move up. They are like displaced by heavier gases, so they move up. Okay, so they become lighter. So, and that contributes to that is due to the change in temperature, which affects the volume, okay, as well as the density. It affects the volume of the gas as well as the density. So this particular issue is very vital as well. Okay, so we need to understand all these three: the coefficient of compressibility kappa or EV, and then the compressibility, which is the inverse of the kappa, and then the coefficient of volume expansion or volume expansivity, which is beta. Okay, so here you can see alpha is 1 over kappa. So meaning for incompressible fluid, alpha is going to be very, very small, very, very small, because of the fact that the change in volume is very small despite the change in pressure. While for incompressible fluid, kappa is going to be extremely high, isn't it? Because you have dV at the denominator. So the change in volume is very small despite the huge change in volume that may occur. Okay. Now, just a few examples here, just to demonstrate the application of the formula. Here you have the bulk model. We are to find the bulk modulo of elasticity of ethyl alcohol is provided as 1.06 times 10 to the power of 9 Pascal. For water, it is 2.15 times 10 to the power of 9 Pascal. Which of these fluids is easier to compress and why? So who can tell me? You have water, ethyl alcohol, and water. Their bulk modulus of elasticity has been provided. So which of these, based on the bulk modulus of elasticity, is easier to compress? And tell me why. Yes, you can talk. Your audio has been enabled. So just talk to me. Just look at the values and tell me. No need to do any calculation here, please. Okay. Yes. Gentlemen. Ya Shabab, are you there?
We are with you, Doctor. Yes.
Yeah. Now tell me. Some are writing. Let me check what you are writing. What do you mean by yes? Yes. No, you should tell me which one of them. You have ethyl alcohol and water. Which one is easier to compress? And then you tell me why. So just tell me, talk to me.
Alcohol, doctor. It's easier.
What? Which one?
Alcohol.
Why is it easier?
It's not easy, but it's easier than
Why is it easier? Why is it easier?
because it's 1.06.
So what do you mean because it's 1.06? Can you explain again? Why? I mean, just because it is 1.06, or do you want to say something else? Or do you want to expatiate more?
This is the ability for compressed, doctor.
Yes, you say it's 1.06, but I mean, what does the value? I mean, you need to add something to that. Can someone help you out? Or can you? Yeah, it's 1.06. All I want you to say is that it's less. It has less. It's bulk
Less
molecules
ability of compress than
water.
yeah.
No, it is easier to compress because its value, its coefficient of its modulus of bulk modulus of elasticity is less than that of water. So it is easier to compress. Simple, isn't it?
That's what I said.
No, you are mentioning the value, so that's why I said you need to complete the statement. Okay. All right. Thank you. So now, yes, ethyl alcohol is easier because its bulk modulus of elasticity is less than that of water. So you can easily compress it. It's easier to compress than water. Now, we are just talking about pressure, change in pressure, incompressibility of water. We still have in our system where sometimes the density of water could change, okay? We said water is incompressible because its density does not change. But when water flows in a pipe, sometimes due to some sudden change, or when a valve is suddenly closed, okay, water is compressed. It's compressed, locally compressed, okay, such as sudden closing of a valve. So it is locally compressed, and when it is compressed, it means its pressure could drop, could reduce, and when the pressure reduces, it makes huge sounds, and that is called the water hammer, as if hammering the pipe. Okay, that's why it is called water hammer. Okay, hammer, is something that we used to, like hit a nail, or something. So imagine yourself hitting a pipe, gang, 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 so it will be making some sound. Okay, so small changes, small density changes in liquids can still occur, or can still cause interesting phenomena in piping systems, such as water hammer, which is characterized by a sound that resembles the sound produced when a pipe is hammered. This occurs when a liquid piping network encounters an abrupt flow restriction. Abrupt meaning sudden, a sudden flow restriction, okay, such as maybe a sharp bend, or you suddenly close a valve, okay, and the fluid is locally compressed. The acoustic waves that are produced strike the pipe surfaces. bends and valves as they propagate and reflect along the pipe. And this, they can cause the pipe to vibrate and produce the familiar sound. Okay. In addition to the irritating sound, water hammering can be quite destructive. It can lead to leaks, okay, and even structural damage because of the reverberation, okay, because of the propagation of the waves which reflect along the pipe, okay, it can cause structural damage. The effect can be suppressed with a water hammer arrestor, which is a volumetric chamber containing either a bellows or piston to absorb the shock. So what we're saying, you can reduce the water hammer by using water hammer arrestor. Wherever you feel probably water hammer can occur, then you can install water hammer arrestor to absorb shock. Otherwise, if the shock is not absorbed, then it can cause structural damage. It can lead to leaks. Okay. Now, water hammer, this is an example. This is a tower, a large surge tower built to protect the pipeline against water hammer. This is built for penstocks. Penstocks are large diameter pipes for, let's say, power generation. They are large diameter pipes. Okay, so, and water hammer can lead to structural damage, and we don't want to have structural damage when, in our hydro power stations. So this is a tower which has, it has liquid inside, water inside, which is open to the atmosphere. Okay, the water inside is open. It absorbs the water hammer shock. Okay, so for large pipes that carry liquid, like, okay, this I just mentioned, this is called surge tower, and it has a free air surface. And then this is another one, okay, which is much smaller, arrestors used for supplying water to a household washing machine. You see, here it contains, it's called a closed hydraulic accumulator tank, which has a gas which is in form of compressed air or nitrogen that is used to soften the shock. Okay, so this is on small pipeline, and this is on very large diameter pipeline called penstocks. Okay. Now, example, here we have, just the example of the bulk modulus of elasticity. Okay, here we have a pressure applied to be 2.15 times 10 to the power of 6 Pascal to a mass of water that initially filled a 2,000 centimeter cube volume. Estimate its volume after the pressure is applied. Okay, so we want to find the final volume here. This is the applied pressure. Okay, and this is our initial volume. Okay, and we want to find the final volume. So V1 is 2,000. Okay, and we want to find V2. And we have our dP, the applied pressure. Okay, and this is water, right? So we know the coefficient of compressibility of water. Okay, so all we need to do is to find dV. Okay, and dV in this case here is minus because the pressure is inversely proportional to the change in volume, meaning when the pressure increases, the volume decreases. So that is why we put the negative sign, so that the bulk modulus will turn out to be positive. Is that clear? Because dP and dV are inversely related. Okay, when the pressure increases, the volume decreases. When the pressure decreases, the volume increases. Okay, so for that, this term dP dV will turn out to be negative. So we put this negative sign to make the bulk modulus of elasticity positive value. Okay, so here we make it the subject, because all we need is dV, okay, which is simply going to be minus dP over EV divided by the initial volume, which is V1. Okay, and once we obtain this value, because dP is given, EV for water, we know the value, we just saw the value now, the bulk modulus of water, okay, 2.2, the bulk modulus of water, the bulk modulus of water is about 2.15 times 10 to the power of 9 Pascal. Okay. Okay. So here we'll just substitute this value here. Okay, which is 2.15 times 10 to the power of 9. Okay. Oh, this is 6. So this is for the pressure, and then this is for the 2.15 times 10 to the power of 9 over the initial volume. Okay, over the initial volume, 2000 centimeter cubed. That is simply 2 liters. Okay. Okay. Let's leave it as 2000. Okay. And then from here, once we find this, dV is equal to what? Just V2 minus V1. Okay. So dV here will be negative. Okay. It is going to be negative, the change in volume. Okay. And then we add, we want to find V2. So V2 simply going V1 plus the change in volume. Okay. V1 plus the change in volume. Okay. And the change in volume, did someone compute this one? Did you find what is the value here? Okay. Definitely this will cancel that. Okay. So this will become 10 to the power 10 to the power minus 3 times 10 to the power of 3 times 2. Okay. Times 2. So this is going to be simply minus 2. Okay. And here we will have, what did I press? Okay. So this is just going to be V1 is 2000 and dV is minus 2. Okay, so this is 1998. Okay, so this is the change in the new volume, centimeter cube. Okay, this is the new volume when you apply that pressure. You see the volume has slightly decreased, slightly. Okay, is it clear? Yo, Shabab, is it clear? Now this one is saying calculate the pressure increase that must be applied to ethyl alcohol to reduce its volume by 7%. Okay, to reduce its volume by 7%. This 7% is now the fractional change volume. So what is the pressure that must be applied? Very simple, straightforward, and direct. This is already given. Okay, we want to find the pressure to be applied. Okay, dV by V is already given, which is 7%. So we change it to decimal 0.01, which is the fractional change in volume. So the volume has been reduced by 7%. Okay, so it is very simple, straightforward, and direct. Okay, so this dP, the pressure is now going to be EV minus EV dV divided by V. Okay, correct? E is 1.06 times 10 to the power of 9, and then the change volume, which is negative, definitely is going to be minus, okay, because it's reduction, because V2 is less than V1, so definitely it's going to be minus, okay, is 0.01, okay, 0.07 times 1.06 exponential 9, okay, so the pressure, the change in pressure that will produce this change in volume engineering is now 7.42 times 10 to the power of 7 Pascal. Okay, very simple. Okay, now that is the bulk modulus or the compressibility. Now we will look at another interesting property of fluid, or in particular here, this property is specific to liquids. Okay, specific to liquid. Okay, surface tension. Surface tension, which is, you know, the liquids, the surface of liquid sometimes it behaves as if it were in tension. Tension meaning it is being pulled from the inside, okay? So liquid possess the properties of cohesion and adhesion due to molecular attraction, okay? This you must have done in physics, okay? Cohesion, the cohesion force and adhesion force, okay? When you have molecules of the same substance, let's say water, the force of attraction between the molecules is called cohesion force, okay? Or cohesion. Is that clear? They are attracted by cohesion, okay, or cohesive force. While when you have molecules of different substances, let's say you have water and glass, okay, so the force of attraction between these two molecules is called adhesion, okay? Okay, so depending on which one is heavier, then that, you know, allows the surface of liquid to behave as if it were an elastic surface. Okay, for gases, usually because of the fact that the molecules are far apart, so they don't, their cohesion force, their cohesive force is very weak. Okay, so they don't have like intermolecular attraction, more or less, but they collide with each other every now and then because they are randomly in motion and constantly colliding with each other and colliding with the walls of their containing vessels. Okay, so this sort of exacts, you know, some kind of interaction among the molecules. But for liquids in particular, whose molecules are closely packed together, are very close to each other, okay, you have strong cohesion. Okay, now, due to the property of cohesion, liquid resists small tensile forces at the surface or at the interface between the liquid and air, known as surface tension. The notation we use for designating surface tension is sigma. Okay, so these are liquids, okay, liquid particles that are attracted by other liquid particles within the water or within liquids, okay, because you have the liquids all over. So this particle is attracted by all particles around it, surrounding it. That is for particles within the water body. But for particles at the surface, they are attracted only by particles within the liquid. Okay? They are attracted by particles within the liquid. Above the liquid, they have different particles, which is air. And air, like I said, because it has less, I mean, the cohesion in the in gas is very small compared to that of liquid. So there is less force that is attracting the liquid particles for those that are at the interface, at the surface. Hence, they are like pulled inward by the liquids within the liquid itself, deeper down. So they are like pulled inward and they behave as if you have like a gelatinous surface, okay? So they behave as if, you know, the surface is under tension. Now, surface tension is defined as the force per unit length, okay, and its unit is Newton per meter because it's force unit length. And then it can also be defined as the energy required to increase the surface area of a liquid per unit area. Okay, the energy required to increase the surface area of a liquid per unit area. Its magnitude typically ranges from 1 to 100 millinewton per meter. So it is really very small, but it has significant influence, as we are going to discuss about some few applications of the surface tension. Okay, you can see the magnitude is very small. 1 to 100 millinewton per meter. The first M here is for milli, okay, and this is for meter, Newton per meter. Okay, milli, that's 10 to the power of -3, very small. Okay, molecules deep within the liquid repel each other because of their close packing. Okay, they repel each other because of their close packing. Now, examples of surface tension, like I said, the value of surface tension, if you look at it, is very small, but it has significant influence. Okay, it has a lot of application in our daily lives and a lot of industrial application. Wicking, water will wick into a paper towel when have water. Use a paper towel. Water will like suck by the paper towel. Ink will wick into paper. Okay, and propylene, which is an excellent fiber for cold weather aerobic activity, wicks perspiration. Wicks here, we mean it sucks. Okay, it sucks away perspiration, that is sweat, from our body. All this is because of surface tension of water. Okay, and capillary rise. Here, a liquid will rise in a small diameter tube. Water will rise in soil. When you have small diameter tube, like up to 1 centimeter, when you just put it inside a container of water, it will rise. The water will automatically rise above the water surface in the container, and that is because of the surface tension. Okay, because the attraction, the adhesion is greater than the cohesion. Okay, the adhesive forces, that is the force between the molecules of water and that of the glass, is stronger than the force holding the water molecules together. That is the cohesion force. Is that clear? So that is why water rises in glass, while for mercury is the reverse, because the cohesion force is greater than the adhesion force. Okay, so water, when you now put a small glass in a container of mercury, the level of the mercury in the capillary tube is going to drop. Okay, because mercury is so strong, it doesn't want to like wet the glass. Okay, and that is why in the first instance water wet glass while mercury does not. Okay, because mercury has strong cohesion force. Okay, its cohesion force, that's the force holding its molecules together, is stronger than the adhesion force, which is the force of attraction between the molecules of the mercury and the glass. Okay, so water rise in soil also due to the capillary rise. Okay, soils, roots of plants buried in soil, they absorb water from the soil due to capillary rise through the tiny roots, pores, openings in their roots. Okay, so the water rises from the soil, to the stem of the plants. All this is due to the surface tension of water. Okay, and you have the capillary instability, where a liquid jet breaks up into drops. Okay, liquid jet, when you throw water, it breaks up into liquid drops. And drop and bubble formation, water on a leaf beads up. It beads up, meaning they collect together and form like a bigger one. Okay, a leaky faucet drips, and sub bubbles form. All these are due to surface tension. Excess pressure. The pressure inside a water drop is higher than the ambient pressure. Okay, the pressure inside a vapor bubble during boiling is higher than ambient pressure. Ambient pressure is the surrounding pressure. Okay, so the pressure inside the water drop is higher. Just imagine when you have a balloon. Okay, when you have a balloon, when you fill it, let's say, with water, or air, so the air will be acting on the sides of the balloon inside. Okay, they will all be pushing on the walls of the balloon from the inside, okay? So the pressure inside is higher than the ambient pressure, which is atmospheric pressure, okay? So as we are going to call that pressure later, we'll call it gauge pressure, which is the pressure above atmospheric pressure. Walking on water, the water strider, which is an insect which can walk on water, okay? Similarly, a metal paper clip or a metal needle. A needle can be positioned to float through the action of surface tension on the surface of water. You can place a needle gently on water and it will stay. Not because of the fact that the density of the needle is lower than that of water. No, density of needle is higher than the density of water. So ordinarily it should sink. But if you gently place it, you can place a pin, a metal paper clip on water and it will stay. It will float. You can make a needle to float on water. And this is because of this small force or the surface tension of water, which tends to allow the water surface to behave as though it were an elastic surface. Okay, we know it's not elastic, but because of the surface tension, it makes the surface of water behave as if it were an elastic surface. Detergents, soaps and detergents also, they improve the cleaning of clothes because they lower the surface tension of water. Okay. How do they lower? They lower the surface tension of water because they introduce other particles that will now reduce, the cohesive force between the water molecules, and that will now reduce the surface tension of water. Okay, and when they reduce the surface tension of water, water can easily move through the pores, the tiny openings of the fabric, that is the tiny openings of your cloth, for effective cleaning. Okay. So all these are different applications of surface tension. So molecules at the surface, like I explained before, are less dense and attract each other. Okay, since half of their neighbors are missing, the mechanical effect is that the surface is in tension. This is molecule deep inside the water, which is attracted from all sides. This molecule at the surface, there is no molecule attracting it. Okay, no molecule attracting it. Of course, we have the air molecule, but unfortunately, the air molecules, like I said, their cohesive forces are less stronger. It's almost absent because the molecules of the gases are far apart from each other. Okay, so there is there is virtually less attraction from the surface. Okay, while you have huge attraction from the molecules inside the water. Okay, so that will now make it like draw the molecules a bit down, okay, to make it behave as if it were an elastic body. So this molecule, one is deep inside, okay, a molecule inside the liquid, and one on the surface. Okay, the one inside is attracted from all sides, while the one on the surface is attracted only by molecules inside the water. Okay, now in the liquid, okay, so this will make it have the meniscus effect, okay, which is this, the meniscus effect. Not to make it flat, it will like sag, okay, it will be pulled towards the water, pulled inside, from inside. Okay, so a molecule is surrounded by other molecules, and intermolecular forces are symmetrical and in equilibrium. That is for figure A, the one that is inside, like this one, like this is figure A. Okay, and then for the other one, which is B, like this one, this is now B. Okay, in which there is imbalance of forces of molecule at the surface. Okay, and this leads to the meniscus effect. So at the surface, a molecule has this force acting only through 180 degrees. Okay, 180, that is from here to here. Okay, the imbalance forces means that the molecules at the surface tend to be drawn together, and they act rather like a very thin membrane under tension because they are pulled by the molecules inside. So this causes a slight deformation at the surface of the liquid, which is called the meniscus effect. Okay, surface tension can be defined as, so F subscript sigma. So it's the surface tension coefficient times the length. Okay, so surface tension force, then surface tension coefficient, which is for water is 0.073 or 73 millinewton per meter. Okay, this is 73 millinewton per meter, and L is the length of a line that lies along the surface of the liquid, and the surface tension force acts on the surface It's the surface force, okay? It acts on the surface. It acts along the surface, okay? So this is like in case of mercury, in which you have the upper meniscus. You know, the other one we call it lower meniscus, and this is the upper meniscus. Okay, in which for water it sags, but for mercury, you know, it curves upward like this. Okay, because of the fact that it has very high cohesive force. Some useful facts about surface tension. Surface tension of water decreases with temperature. Why? Because when you have higher temperature, when the temperature increases, the molecules gain more energy to now vibrate and move further apart. So once they are energetic, they move further apart, you know, in random, their random motion increases. They move more like randomly, more randomly, and that effectively reduces the cohesive force. Okay, that is the force of attraction between the molecules reduces. Okay, as such, the molecules can move like faster, and that is why, like we also mentioned in the case of density. Okay, when you increase the temperature, you know the molecules expand. They expand, and the cohesive force reduces. That is the force binding them closely together reduces. So they move like further apart, and that reduces the cohesive force. Okay, which will eventually increase the volume when you increase the temperature, and then the density reduces. In this case, the cohesive force reduces, and the attraction, you know, between the molecules within the liquid reduces, and that reduces the surface tension. Okay, and this is like zero temperature. This is the value, 0 degrees 20 up to 100. Okay, so you can see how it reduces the surface tension with temperature. Because thermal expansion of the molecules further apart, okay, this I just explained, and this reduces the average attractive force between molecules. That's cohesive force goes down. Surface tension is strongly affected by the presence of contaminants or impurities. For example, adding soap or water decreases the soap tension. Okay, when you add any impurity, it reduces, because those impurities will go in between these molecules and will reduce or weaken the cohesive force, okay, between the molecules. Okay, and that will effectively reduce surface tension. The reason is that impurities concentrate on the surface, and these molecules do. Okay, this I just finished explaining. Most problems, including surface tension, are involved by drawing an FBD, free body diagram, and applying force equilibrium. You took statics, so you know what I mean by free body diagram and how to sketch a free body diagram and how to apply equilibrium equations. Now, here we have a simple example, which is for applying equilibrium to calculate the pressure rise in a water droplet. I mentioned that the pressure inside the water droplet is higher than the ambient pressure. Ambient pressure here, you know, we're referring to atmospheric pressure if it is in open air. Okay, so the problem statement here states that the pressure inside a water drop is higher than the pressure of the surroundings. Derive a formula for this pressure rise. Then calculate the pressure rise for a 2 millimeter diameter water drop. Okay, use surface tension of water to be 73 millinewton per meter. Okay, so here we are to derive the formula for this pressure rise. And how do we do that? Okay, we have a water droplet, so we take a section, and when we take a section, we reveal the forces acting. Okay, you remember when we take a section, you have to reveal internal forces acting. Okay, so pressure inside a water drop is larger than ambient pressure, and we are given the diameter and the surface tension. So we want to use PI to designate the pressure inside the water drop. When we take a section, okay, we show the forces acting. You have pressure force, FP, acting, and you have the surface tension at the sides, at the surface. Okay, this is the surface tension acting at the circumference, okay, at the circumference of the water drop, okay, at the circumference of the water drop. You have the surface tension, okay, acting, and you have the pressure force acting in opposite direction. So here we apply the force equilibrium. The force due to pressure is equal to the force due to the surface tension. So what is the force due to the surface tension? Sigma. What is L? The length of the circular path, which is length of a cycle, which is the circumference, which is pi d. So that's why you have, sigma L. L is pi d, which is the circumference of a cycle. Very simple. And then what about the pressure force? The pressure force is the pressure times the area, because pressure is force divided by area. And what is the area? The area of a sphere of a cycle is pi d square over 4, okay, or pi r square if we are using the radius. Okay, so we now equate the two and then make P the subject of the formula. So the pressure inside the water droplet, or the droplet, is 4 sigma over D. So now we know sigma 0.073, we know D 2 millimeter. So we just substitute and find the pressure, which is 146. Gauge. Gauge means it's above atmospheric pressure. In chapter 3, we will explain all this. Gauge pressure is the pressure that is above atmospheric pressure. Meaning, if we want to find the absolute pressure, we add atmospheric pressure. Absolute pressure, the absolute pressure, P absolute, is P gauge plus atmospheric pressure. Okay, so you see, gauge is the pressure above atmospheric pressure. Okay, so this one puts Pascal gauge. Yeah, although the pressure is very small because the atmospheric pressure is 101.3 kilopascal, and this is just 146 in kilopascal. This is like 0.146 kilopascal. So very small compared to the atmospheric pressure, but it is higher. Okay, the pressure inside the water droplet is higher than the atmospheric pressure. This is like above atmospheric. Okay, above atmospheric. Now, notice the answer is expressed in gauge. Okay, this I just explained. And the rise, okay, this I also explained the physics behind the rise in the why the pressure inside the liquid drop is increased. Okay, because of the membrane effect of surface tension. Okay, which is, just imagine a balloon. The pressure inside the balloon pushes outward against the membrane force of the rubber skin. In the same way, the pressure inside a liquid drop pushes outward against the membrane-like force of surface tension. Okay, is it clear? Now, weighting action of water. How does water weight anything? Glass, and other stuff. The strength of the capillary effect is quantified by contact angle, theta, okay, which is defined as the angle tangent to the liquid surface, the angle that the tangent to the liquid surface makes with the solid surface at the point of contact. Okay, this is called the contact angle. If this angle is acute, that is less than 90, then it's going to weight that surface. If it is obtuse, that is greater than 90, then it is not going to weight that surface. Okay, so water weights glass because adhesion is greater than cohesion. Okay, weighting is associated with a contact angle of less than 90. Hydrophilic surface is polar. Hydrophilic surface here, that is water, philic, loving, that is water loving surface, is polar. Polar means it likes, water, is attracted to water, just like you have liquids to be polar and non-polar. Polar liquids are liquid that is miscible with water, while non-polar does not mix with water, like gasoline, kerosene. They don't mix with water, so they are called non-polar. So this is an example when you put, a tiny drop of water on a glass or on a surface, it will appear this way. So we said the contact angle is the tangent, is the angle that the tangent to the liquid surface makes with the solid surface. This is the liquid surface, okay? So the tangent, okay, makes with the solid surface, okay? and this is the solid surface. So this angle theta is the contact angle. You see this angle is less than 90. Okay, so adhesion in this case between dissimilar materials, water and glass, is stronger than adhesive, is stronger. Okay, the adhesive forces is stronger than the cohesive forces. So the adhesive force pulls the water outward. Okay, it pulls the water outward. Here you have weaker cohesive force. Okay, and this is why water wets glass, and that is why it produces the lower meniscus. Okay, so it pulls down, and this is the contact angle. Okay, theta or phi in this. Okay, in case when water is in a particular container. Now water beats up a hydrophobic material such as Teflon because the adhesion is less than cohesion in this case. Okay, and how does it appear? It appears like this. Okay, here the angle, the contact angle is greater than 90. Okay, it can be water on Teflon. Okay, because the two materials, Teflon is non-polar or is hydrophobic. The surface is hydrophobic surface. Okay, so it will not appear like glass. So theta is greater than 90, and here in this case the cohesion is greater than adhesion. Okay, so you have stronger cohesive force, that pulls the water into a spherical shape, the water together. Okay, and you have weaker adhesive force in this case. And this is also the case with mercury. That's why water is called, in this case, water is the weighting fluid in the first case because it weights the glass. In the second case, it is non-weighting fluid because it does not weight the surface. Okay, it can be mercury and glass, it can be water on Teflon, and all other non-weighting cases. Now, capillarity. I will take, let's take just 3 minutes break, and then we look at capillarity. Okay, just 3 minutes break. Okay, drink water, relax, and then you come back after about 3 to 5 minutes. Yes, I'm back. So let's move on. Let's continue from where we stopped. Okay. Now we'll continue with capillarity. Okay. That is the rise of water in a small diameter tube. That is the capillarity. The surface tension leads to the phenomenon known as capillarity, where a column of liquid in a tube is supported in the absence of an externally applied pressure. Okay. This happens because of the surface tension of water. The rise or fall of a liquid in a capillary tube is caused by surface tension and depends on the relative magnitude of cohesion of the liquid and the adhesion of the liquid to the walls of the containing vessels. One of the obvious cases in surface tension is capillary rise. Okay, of course, you have capillary rise, okay, when water rises in capillary tube, and you have capillary fall when water falls, or not water in this case, but when liquid falls in capillary tube. In this case, it will be a different one, which is mercury. Okay, we will explain all this. There are two main forces controlling the capillary action: adhesive forces between different molecules and cohesive forces between alike molecules. If adhesive forces are greater than the cohesive forces, liquid will rise in the, just like when adhesive forces are greater than the cohesive forces, liquid weights glass or weight a particular surface. Okay, so here liquid will rise in and weight the tube. If cohesive forces are greater than the adhesive forces, liquid will drop in the tube without weighting it. That is like in the case of mercury and glass, the second case. Like this is the case of water and glass, because water weights glass, and glass capillary tube. And this is the case of mercury and glass capillary tube. Okay, because mercury doesn't weight glass, and that is capillary fall. Okay. Now, adhesive forces greater than cohesive forces, liquid will rise, like in this case, you can see this is the level of liquid in the container. This is small diameter up to like 1 centimeter, okay, up to 1 cm, it will rise. Because the smaller the diameter, the higher we are going to see that relationship. And this is now the surface tension force, which is acting along the surface, okay? This is the surface tension force, this is the contact angle, okay, between the surface and the solid boundary. So adhesive force between the water and the glass pulls the water up the tube. For adhesive forces less than cohesive forces, you have liquid drop in the tube due to capillary repulsion, not capillary attraction in this case, okay, but capillary repulsion. Example, mercury and glass, okay. This is mercury, its level you can see is lower than the level, okay. So this is H, this is H. We will see how to determine H, whether capillary rise or capillary fall, okay. So this is still expatiating. The pull of surface tension lifts the column. Right? So surface tension lifts the column. What about mercury? It pulls it down, okay, or it pushes it down. Okay, the pull, because in this case you have adhesion less than cohesion. Okay, meaning cohesion is greater than adhesion. Okay, so how can we determine the height of water in the capillary tube? We apply equilibrium equation, because it is the surface tension force that is pulling this weight of liquid. Okay, so this weight W is being pulled by the surface tension force acting along this. Okay, so we resolve the force and then balance it with the weight. The weight in the capillary tube is balanced by the surface tension force. Okay, so the vertical component of the force in the z direction, that's the vertical component, is balanced by the weight. Okay, and then we now substitute to find H, okay, or delta H. Okay, let's do that. So here we get our system. Our system is the weight of liquid in the capillary tube. So this is the weight. Weight is mass times weight is mg, isn't it? Mass is what? Density times volume. Okay, density times volume, g. Okay, and rho g is what? Specific weight. Okay, rho g is specific weight. Okay, times the volume. And what is the volume? The volume, this is cylindrical. So the volume will be the cross-sectional area of the liquid, which is circular, pi d squared times, which is the area times the height, which is delta H. That's why you have the weight. You have gamma, this is the area pi d squared over 4 times delta H. And the surface tension force, okay, is sigma pi d, because it is circular. And then cos theta, the component in the vertical direction. When you resolve the force vertically, you have cos theta, okay? So these two forces are equal. Weight is balanced by the surface tension force. Okay, so here we just, make this the sort of the formula. But this angle W is very small. Okay, it's very small for weighting fluids. Assume that the contact angle is nearly zero. This contact angle is nearly zero, and when it is nearly zero, cos theta is approximately equal to 1, because cos 0 is 1. Okay, and this is a good assumption for water glass interface, because the angle is nearly zero, okay, because of the meniscus effect. Okay, so here cos theta becomes 1, and then delta H or H becomes 4 sigma over gamma d. Gamma is the specific weight of water, okay, or just specific weight of the fluid or liquid. So in atmospheric air, the contact angle of water and most other organic liquids with glass is nearly zero. So phi is almost equal to 0, okay, or theta, as the case may be. And note that the contact angle in general is different in different environments, such as another gas or liquid in place of air. So here is the water-air interface. If you use another gas, the contact angle will change, okay? So it depends on the medium, on the gas or liquid, okay? The contact angle changes from one medium to another. What about capillary fall, okay? Capillary fall. For capillary fall, this is for capillary rise, H is greater than 0, okay? For capillary fall, it is going to fall, so H is less than 0. H will be less than 0 because in this case, theta is going to be more than 90. So we cannot ignore it, okay? And theta, cos theta is going to be minus, okay? Note that capillary rise is inversely proportional to the radius. You see, this is diameter, which is twice radius. Diameter is twice radius. So the capillary rise is inversely proportional to the radius of the tube, meaning that the smaller radius will have higher capillary rise and bigger radius will have less capillary rise. That's why, like, up to about pipe size or tube of 1 centimeter, you can have some capillary rise, but once it exceeds 1 centimeter, hardly do you find any appreciable capillary rise. Okay, therefore, the thinner the tube is, the greater the rise or fall of the liquid in the tube. Okay, in practice, the capillary effect of water is usually negligible if tube whose diameter is greater than 1 centimeter. And like I said, contact angle of mercury is not almost 0. Okay, hence cos theta is not equal to 0 degrees when you have capillary fall. So for capillary fall, it's the same formula, but we have to maintain our cos theta here. Okay, our cos theta has to be maintained because cos theta is not equal to 1 when you have capillary fall, because theta will be more than 90 in almost all cases, like 130. And cos 30, cos of angle more than 90, you find it to be negative. So that's why you have it to be minus. Okay, so when you have it minus, it means capillary fall. Now, still on the droplet, okay, the water drop or droplet. Okay, so we will analyze it. We have analyzed it before, but we will also now make some comparison. Half of a droplet or air bubble, okay? So you remember we did the surface tension forces acting along the surface, okay? And this is balanced by the pressure force inside, okay? Or the change here, we use delta P, okay? Delta P is, see, now the pressure inside minus is the pressure difference. This is the internal pressure minus, the ambient pressure, the surrounding pressure, which is usually atmospheric, okay? So now we balance it out, okay? This is pi r squared. If we're, okay, pi r squared, the area of the cycle, and this is the circumference of the cycle. You remember surface tension force is what? The force is sigma L, and this is sigma L. In this case, is the circumference of the cycle, which is 2 pi r. Okay, So the surface tension force is balanced by the pressure force, okay? And the pressure force is the pressure times the area, okay? So this is equal to that. And then we make delta P to be the subject of the formula, which is 2 sigma over R, okay? If we are using R. If we are using D, because R is equal to D over 2, we have 4 sigma over D. 4 sigma divided by D. So this is now the pressure difference, okay? This is the internal pressure inside the droplet, and this is the P naught is the surrounding pressure, okay? So which is atmospheric. So if you are using the gauge pressure, you just strike this out, because for the gauge pressure, the atmospheric pressure is the reference, which is now 0, okay? Where Pi and P naught are pressures inside and outside of the droplet or bubble. Again, if it's not atmospheric, if it's another gas whose pressure will be provided, so it will not be 0. So in that case, you use the pressure and find the pressure inside the droplet, okay, or bubble. Now, what about if it is a sub bubble, half of a sub bubble? For half of a sub bubble, there is extra factor of 2 in the first balance for the sub bubble, okay, due to the existence of the sub film. There is sub film with 2 surfaces. You can see the 2 surfaces, inner and outer surface and inner surface. While for the droplet, you have just one thin layer, okay, one thin surface, okay. But for the sub bubble, it is wider, okay. So in that case, you have to have the surface tension acting on the inner surface and the outer one. So here the circumference is going to be 2, okay, because you have the inner and the outer. While for the water droplet, you have just one thin surface, okay. So in this case, in the first balance also, we now use 2, okay, and it turns out to be 4 sigma over R. This is 2 sigma over R, okay. So we have to note the difference, you know, for a droplet as well as a sub bubble. Now another example here, calculate the capillary rise for water at 20 degrees in a glass tube whose diameter is 1.6, okay. So this is the specific weight of water, okay, or the weight density of water, and this is the surface tension of water. We want to find the capillary rise. Very simple. This is the formula: 4 sigma over gamma d. Okay, and we just substitute the values, okay, to get this one. Okay, if you remember this capillary rise, so there is cos theta here, which is negligible. Okay, in this case, but if it were to be capillary fall, we will have to introduce our cos theta, because cos theta is not negligible in that case, okay, because theta is not 0. Here you just substitute the values, you know, all the parameters are given. Sigma is provided, gamma is provided here, d is also provided. 1.3, 1.6 millimeter, but you have to convert it to meter, which is 1.6 times 10 to the power of minus 3, okay, and get the height. Now here it says a 2 millimeter glass tube contains mercury with air above at 20 degrees. What will be the capillary depression? Okay, for mercury you have capillary, for water you have capillary rise. Assume contact angle between mercury and glass to be 130. I told you it's more than, you know, it's high, 130, more than 90. And the surface tension of mercury exposed to air is 0.51 Newton per meter. Okay, so it's the same way. Like I said, here you will have minus. Okay, so we introduce this minus sign so that delta H will become positive at the end, because cos theta was 180 will give us minus. Okay, so the minus will take care of this minus sign, and our delta H will turn out to be positive. Okay, so all the parameters have been provided. This is the surface tension, which is provided here, and then we have, this is our theta, and then this is D, the diameter, 2 millimeter, which watt meter, and then we have the specific weight of mercury. Okay, specific weight of mercury is rho g. The density of mercury is 13.6. Okay, I think that is it times 10 to the power of 13.6 times 10 to the power of 3. Okay, 10 times 9.81. So this you get this. Okay, and then when you plug the values here, you will get delta H. Okay. Now this is another problem in which we are asked to determine the size of sewing needle that can be supported by surface tension. I told you, due to the surface tension of water, you can gently place a sewing needle. Okay. The internet shows examples of sewing needles that appear on to be floating on top of water. You can Google such video clips on YouTube. Okay, this effect is due to surface tension supporting the needle. Here we are to determine the largest diameter of sewing needle that can be supported by water. The largest diameter that can be supported by water, and we are to assume that the needle material is stainless steel with specific gravity of 7.7. Okay, so we are determining the largest diameter. So this is like a cross section of the needle. Okay? So you have water, so it will depress the water surface gently due to the surface tension. So assume the sewing needle is a cylinder and neglect end effects because the ends are not cylindrical per se, they are tapered in a way. Okay, so assume that it is a cylinder, and then the water properties, you have the surface tension, the specific weight, okay, and this specific gravity, the specific weight of water is provide for the stainless steel. I mean, this is the relative density specific gravity times the density of water. Okay, which is simply you remember gravity is what is gamma of any substance. Okay, let me say material over gamma of water. Okay, so this has been provided here for the needle. This for water is 9810, okay, because it is the density. This water is the density times G, which is 9810. Okay, the specific weight of water. So this will enable us to get the specific weight of the needle. Okay. And then we want to find the largest diameter of the needle that can be supported. Here we have to draw the free body diagram of the needle supported by the surface tension, okay, and select our system, okay. So this is the needle, the weight of the needle acting vertically downward, the surface tension acting the surface. You can see that at contact angle of theta. So we have to resolve it vertically. So the weight of the needle will be supported by the surface tension, just like we did before. The weight of the water in the capillary column is supported by the surface tension. Okay, and the surface tension here will be acting. The formula for the surface tension is sigma L. And what is that L? L is the length acting is 2L cos theta. 2L is the length of the needle. Okay, this L is the length of the needle because the needle is in contact with the, at two ends. Okay, the surface tension is acting at this end and at that end. Okay, so L is the length of the needle, and cos theta is when you resolve the surface tension vertically. Okay, this cos theta is because of resolving the surface tension vertically. So this is our surface tension force. Now we should evaluate the weight. Okay, the weight, which is weight over volume times the volume, or the specific weight times volume. Simple. Okay, and we have the specific weight of the needle, and the volume of the needle is the area, the cross-sectional area, which is circular, pi d squared over 4 times its length. So we now equate this B to be equal to C. Okay, and what do we want to find? We want to find D. So we can make D the subject of the formula. All other parameters are already provided. Okay, So here D is equal to square root of 8 pi over 8 sigma over pi gamma. Okay. So when you substitute, we have the value to be 1.7 millimeter, 1.57 millimeter. When applying specific gravity, look up water properties at the reference temperature of 4 degrees. Okay, because at this temperature you have water to have its highest density. Okay, so is this clear? Now, vapor pressure. I have started explaining vapor pressure. Vapor, I have started explaining vapor, when liquid changes from liquid to gas, we call it vapor, okay? And although here I will be most concerned about the water vapor, okay? The vapor pressure due to water in particular. But vapor is generally, the gaseous form of any material that, emanated from its liquid form, okay? Or sometimes it can emanate also from the solid form when you have sublimation taking place. Okay, so vapor pressure is the pressure at which liquid vaporize or boil at a given temperature. Okay, when liquid vaporizes or boil, they form bubbles and then you have vapor coming out when you are boiling water. Okay, so it's the pressure of the vapor. Okay, that's why it's called vapor pressure. It is the pressure at which the liquid phase and the vapor phase of a material with thermal equilibrium. Thermal equilibrium here, it means there is no net flow of thermal energy, meaning they are at the same temperature. It means the liquid and the vapor are all at the same temperature. Okay, there is no net flow of energy between them. As external pressure on water bodies reduces, okay, vapor pressure reduces accordingly, boiling point of water as well. So what are we saying? As external pressure on water reduces, vapor pressure reduces, and accordingly, boiling point of water as well. Okay, when you have the external pressure reducing, we explained the atmospheric pressure, which is the gases surrounding the atmosphere, surrounding us, that are pulling on us. I mean, they are pushing. They are pushing on us. Okay, thereby exerting pressure on us, called atmospheric pressure. The same thing when you open liquid, there is atmospheric pressure acting. Okay, so when you now reduce that pressure, okay, when the external pressure on water reduces, the vapor pressure reduces as well. Okay, and then accordingly the boiling point of water is reduced, because it means the molecules at the water surface will find it easier to move to the gaseous phase, because there is no pressure like pushing on the water surface that's preventing the water molecules going into the gaseous phase. Okay, now so when the vapor, or when water molecules find it easier to escape from the surface of water, it means the vapor pressure can easily form. And when it forms, it means you can easily boil. Okay, so the boiling point of water will reduce, because boiling point is simply the fact that the vapor pressure is equal to atmospheric pressure. A liquid boils when its boiling point is equal to the external atmospheric pressure, or the standard atmospheric pressure. Like water, it boils at 1 atmosphere. Okay, when the vapor pressure, or the saturated pressure, which we call the vapor pressure, is equal to the atmospheric pressure, when water begins to boil. So when you now reduce the pressure, the atmospheric pressure, it means water can easily boil at lower temperature. It can boil at lower temperature. The same thing when you increase the atmospheric pressure, or the pressure acting on the liquid, it means it will boil at higher temperature. And this is what happens in pressure cooker. Okay, in pressure cooker, because of the pressure acting on the steam, air is expelled. So the steam is contained inside, okay, which exerts pressure on the liquid, thereby increasing its boiling point. So the liquid inside can be held in liquid state for more than at 100 degrees Celsius. So now, is it better to cook in Jeddah or the Himalaya? The Himalaya is a mountainous region in the Southeast Asia, thereabout. Okay, it's a mountainous region where you have, high altitude. The mountains are very tall, while Jeddah is at sea level. So at the Himalaya, which one will boil? I mean, where is it better to cook? Is it in Jeddah, where you are at sea level, where the pressure is atmospheric, or at the Himalaya? The Himalaya, definitely the pressure will be less than atmospheric. Okay, the pressure will be less than atmospheric. For that, water will boil faster. Okay, water will boil faster. So definitely it will be easier to cook in the Himalaya than in Jeddah, because in Jeddah, water has to reach 100 degrees Celsius before it can boil. While on the Himalaya, it may be, let's say, 60, 70, 80, depending on the pressure. Okay. And vapor pressure is also called saturation pressure. Okay. And the corresponding temperature is called saturation temperature. Saturation, it means that, the pressure and the liquid molecules are in thermal equilibrium. Okay, or the fact that the amount of liquid, of molecules going into vapor is equal to the amount of molecules coming back to the water surface. Okay, so there is some saturation. By saturation here, there is no net flow of thermal energy, meaning the molecules in the liquid and the gaseous phase are in thermal equilibrium. Okay, so we call it saturation pressure, which is simply the vapor pressure. Okay, and the corresponding temperature is called the saturation temperature. So the saturation pressure for water is 1 atmosphere, isn't it? And the saturation temperature for water is 100 degrees Celsius. You cannot boil water above 100 degrees Celsius. Once it is above 100, it will have to change to gas once it reaches 100 degrees Celsius, unless you increase the saturation pressure, okay, by increasing the atmospheric pressure acting on the water surface. However, the time required to reach vapor pressure or water is much less in conditions with higher external pressure. Yeah. Oh, my alarm is ringing, so time for the quiz. It's time for the quiz. So I will stop here. I will update this material and upload. Okay, so please, even if you downloaded it before, download this chapter again, because I added some few things here and there. Okay.
Doctor, about the quiz, do we have to change it to PDF or upload it as a photo?
Yeah, you can just upload it as photo, but scan it very well. Okay, make it clear and write your ID clearly.
Inshallah.
Yeah. So now I will make the quiz available so that you can.
I still wish you make it more longer. If it's
No, but you didn't see the question, so I know the question. That's why
it's nervous to be the first quiz and to take it in 10 minutes.
No, this is if you are in class, I mean, I can give you more time, but this is online quiz in which I cannot control what you check. You check your book, you check online, you do this. So the shorter the time, the better. If it is in class setting, then I can give you longer time, because that one I know everything is going to come from your head. But this one is online. I cannot control what you check, what you do.
But I will cheat, Doctor, but he will cheat even if it was 2 minutes. And the people who cheat, it's easier to them.
What?
It's in 10 minutes. And the opposite for those people who are studying, because they still need more time, because it's the first time they take this course.
Yeah. Don't worry. Do it, and then let's get your feedback on that. Okay?
Okay, inshallah. Thank you.
Yeah. So now I will make it available. And don't forget, you are to upload it back. Okay? So now it is available. So wish you good luck.